Hi, everyone, and welcome to OPAL-RT Learning Journey. Today's session will be about onboard charger, OBC, as we call them, and how to bring the OBC models to real time. So I'm very glad to welcome you today for this webinar. I'll be with my colleague, Hamza. So Hamza Soleimani, as an electrical engineer, that will be presenting the demo, and myself, Sébastien Sans, I'm offering manager for the energy conversion market. I'm going to be presenting like the OBC technology that we are targeting with our product. So for today's agenda, so I'm going to start with a quick introduction about OPAL and what we do for our automotive customer. Then I'm going to move to a quick presentation about OBC simulation in real time with our platform. Then we'll see a quick demo of Hamza, who has brought actually an onboard charger model in real time with our solution. And we'll have a short period of question at the end of this webinar session. Please during the course of the presentation, don't hesitate to type in your question into the question and answer section of this webinar, and we'll look at them at the end and try to answer as much as we can. So first of all, OPAL-RT's automotive solution. So we can regroup them into three main categories. So we have the charging, the propulsion, and the battery. Today's subject will be about charging. So how can we emulate on a real-time simulator for HIL application, what we call the onboard charger? So there is many challenges in power electronics nowadays, and even more in automotive. So the first challenge that the automotive vendors are facing is vehicle integration. So how a converter design can be extremely compact. Like the team of Valeo that we worked with for the past years, they had great challenges in making their product as compact as possible in order to fit various cars, but also keeping it efficient. So how can a product that has been designed that compact can be also efficient and have a good thermal and losses management inside? And let's say the third challenge I see would be all the standards of the industry that we need to follow. The product has to be very reliable. And for example, there is also standard regarding to the current ripple that the product must meet. So let's come back to the power electronics itself. So, and the electronics in general. So I'm sure you know it. There is a law which is called Moore's law, which is a law that defined the number of calculations per second per $1,000 you could do with a product. And from the start of the industry, I mean, that number kept growing, okay? We were capable to make smaller silicon circuits and to achieve better performance over time. That transition in microelectronics obviously impacts a lot the power electronics in some ways. So we have seen the same kind of transition for the power electronics, where we see that, for the same level of power, now with the new semiconductor technology, we are capable of switching at higher frequency. And in the car industry, this is very, very interesting because it opens doors to topologies that we couldn't really use in the past for this level of power. And basically, on onboard charger application, the chosen technology that was for the design was mainly resonant converter topologies. And this became a standard for onboard charger application because it's very compact and it has a very high power density because it switches only when the current crosses zero. Obviously, this wouldn't be we wouldn't be capable today to make this kind of design if you would have stayed to the old, let's say, type of power electronic switches that existed in the past. Now we are capable to implement silicon carbide and also GaN devices for wide application. Devices that was reserved for the RF industry before now can be used into power electronics in cars. The resonant converter principle is that you're going to have a pretty high switching frequency. So in that example, I set it to 300 kilohertz. And we'll have a resonance occurring inside of what we call the resonant tank. That resonance will create on the secondary side of the transformer. So we're going to rectify that current, and then it's going to work as a DC-DC converter as a function of the switching frequency. And the reason why we have such high frequency into that converter is that we can reduce the transformer side. So as I said before, integration and size, of the OBC is key for customers in this kind of applications. And so by having such high frequency reach, we can reduce the transformer size and then have a very compact design and very efficient design. Now, let's look at how we control a LLC resonant converter. So it's a converter that is controlled using the frequency that is applied on the gating signal. And now we are controlling with the frequency and not with the amplitude. If we are looking at other power converter technology, like such as VSC, voltage source converter, then it's an amplitude control device. Here it's a frequency control device. And obviously this causes some challenges in the simulation. The first challenge is the resolution that you need on the switching event. The resolution that you need when you capture a switching event in the simulation has to be very, very large. So for example, in that example, if you capture, like a 40 kilohertz signal with a 5 nanosecond error on it. So let's say you would sample the digital N with the 5 nanosecond, clock. You would get 100 hertz of error, in your capture. But this, when you look at the gain, when you look at the gain V out versus the VN, the input voltage, it could lead to a few amps, at the output of error. The thing is that aliasing that you create with the digital simulator will create a ripple on the current at the output stage of your DC converter, which cannot be, acceptable for the test that you want to do. So in the case of the resonant converter, it requires a very, very high resolution and compensation on switching event to be simulated accurately. And so just to wrap up everything, if we compare, what we were doing before in power electronics and what we are doing now, so for VSC control, it was pulse width control. So it was amplitude control. And now we are moving to switching frequency control. The gating signal frequency came from 1 kilohertz to 100 kilohertz. And now it says more than 100 kilohertz and can go up to 1 megahertz. So the simulation challenges are not the same as before. Before, getting the accurate amplitude was very, very important. But now getting the right frequency applied and avoiding aliasing and ripple effect is what makes the simulator accurate. And so the solution that we have proposed with OPAL, that we have worked with Valeo to build, was to actually make a model, a EHS, that has a fast model loop rate with a very, very high resolution of the capture event, of the switching capture events, and compensation in the model in order to reach a good level of accuracy. So let's talk about the OPAL-RT HL testing offering for OBC. So as most of our solution, so we provide simulator, real-time simulator, as the piece that you see in the center of the screen, that is composed by one FPGA and one CPU. For the case of this specific, simulation that requires very fast simulation, we're going to go and go deep inside the FPGA. we have a tool that is called EHS that is, let's say, the deployment of FPGA model on the FPGA device. The real-time simulator will be connected to the device and the test with which is the OBC controller, and you'll be able to see that in the demo that Hamza will show us later on. So what is EHS? So EHS is a product that we've made in 2012 and that we started to develop in 2012. We are still developing new generation from now on to get the power of the FPGAs at the engineer's fingertip. So we knew at the time that not all engineers in the field of testing for power electronics knew how to develop models on FPGA and optimize model on FPGA. So we made a product that from the circuit editor will automatically generate all the equations and download that to the FPGA so the FPGA can act as the model, the power electronics model that the user wants to simulate. What we did for the OBC simulation is that we did a new generation of that EHS device, which is the EHS Gen 5. The goal of that EHS Gen 5 was to deliver the most powerful real-time simulator for power electronic circuits. It can go down to 90 nanosecond time step for user-defined topology, which means you can connect the component how you want. You can do all the topology you want with the provided library blocks in order to build your own and custom OBC topology. It has a 625 picosecond and unmatched gate oversampling with switching event compensation. So we're gonna oversample the gate events and we're gonna compensate in the results of the electrical simulation in order to have a very accurate result. And to do so, to avoid also to create more, inaccuracy in the system, we also added like a fifth order discretization instead of backward standard discretization, as we can see normally on the market of FPGA simulators. It became the fastest real-time reconfigurable power electronic simulator of the world. Obviously, we didn't make that with making some compromise in the user experience. We streamlined the workflow in Simulink as much as possible. You can see on the screen right now how easy it is to load a new circuit into the EHS block and to integrate it into your CPU model. This allows co-simulation with the CPU-based model and SIL-ready simulation in Simulink. You can also integrate your own S function with your own control in Simulink, interface it with your EHS model, and then you're going to be ready for the next stage of development when it comes to HIL deployment of the simulator, because the model will be already made in EHS. Then we also focus on the fact that you can open the schematic editor directly from the block. So when you double click on the block, directly the schematic will open, and then everything is centered around what you want to work with is your schematic, changing parameters, adding more components, adding probes, wanting to debug something particular into your topology. I mean, you name it, you can do it directly from Simulink and from the schematic editor. The schematic editor comes with a various components that you can integrate into your circuit design. And so we have a growing number of components that now are supported with EHS Gen 5. You can put machine, you can put outbridge converter, you can put single switches. And so it becomes very easy to actually reproduce your own electrical topology. Something that is very important also when you want to do an OBC simulation is to verify that all the test scenarios are covered. We have a feature which is called the parameter set, which allows you to modify in real time parameters of the electrical system. So this way you can introduce fault, or you can modify like the load of the system in order to test the system under like disturbances. Also, we still have the test scripting through the RTLab Python API. So you can write a Python script and automate your test like you would do like on the CI/CD system for software design. Now let's talk about RTX Edge. In case you need even a faster model, I mean, let's say 90 nanosecond is not enough for what you need to do, and you need a very optimized solver that will be deployed directly on the FPGA. So we have the RTX Edge Toolbox that allows you to do that. So with our RTX Edge Simulink-based toolbox, you can implement directly on the FPGA customization that you need for your model. This way, you can implement a custom model with a sampling rate of 200 megahertz, which means 5 nanoseconds. Using the exciting system generator for DSP toolbox is directly within Simulink, so you can do your code this way. You can test it offline, you can deploy it on the platform, and the RTX Edge toolbox allows you to access the simulator I/O as you want. So there is the EHS that is more for, let's say, standard topologies. And then if you need something that goes very fast, you have like specific needs on the I/O side with low latency processing needed, then you can implement your own model on the FPGA. So takeaways, the EHS is now capable to simulate fast power electronics such as resonant converter. User-defined converter topology can be simulated in real time down to 90 nanoseconds with a 625 oversampling with the EHS Gen 5. It's compatible with the OP5707XG, OP4610EG, and the OP4512 simulators. And it allows the co-simulation with CPU-based model for like large and slower model with MATLAB Simulink and HyperSim. And also, it can be coupled with optimized custom FPGA-made model. So now let's go and let's watch the demo that Hamza has done and how you can deploy your own OBC on the real-time simulator.
Hi, everyone. Thanks, Sébastien, for the great presentation. So the demo that you will see today will cover the context of onboard charger and what are the potential challenges of simulating it. We'll also see how simple it is to implement this system and monitor the simulation results on the OPAL-RT platform. So without any further delay, let's start the demonstration, and I hope you will enjoy it. Hello everyone, my name is Hamza Suleimani. I'm a sales engineer at OPAL-RT Technology. Today, I would like to welcome you on our OPAL-RT learning journey. During this session, we are going to run our onboard charger real-time simulation on a full HIL setup. Before we start with the demonstration, let's give some context about the onboard charger and what are the challenges of simulating it. What is an OBC? OBC stands for onboard charger. It is a device which is usually mounted inside your electric vehicle, and it is responsible to convert the AC power from any AC source or simply from the grid to the right DC form needed by your battery inside the vehicle. The OBC first stage is usually a boost PFC converter, also known as power factor converter, and the second stage is the LLC converter, which is directly connected to the electric vehicle battery pack. In this case, we can see that the output of the LLC converter is connected to a resistor, which is representing the battery. Let's have now a look to our HIL setup. So first we have the OP4610XG platform, where the plan model, which is the OBC circuit, is being simulated in real time. Then we have the OP8666 controller, in which the control algorithm is being performed. So during the real-time simulation, measurements are sent from the plant model to the controller using the I/O interface of the real-time simulator. Then control is performed and PWM generation occurs at the right frequency and duty cycle. These switching signals are then sent back to the plant model using the I/O interface of the real-time simulation. Then the right voltage and current are generated to charge the battery. Let's now have a look to the simulation results. In this demonstration, 3 different user interfaces are available for the user. The first interface is where the user can monitor few signals from the plant and send commands. So first of all, let's set the frequency for our AC source, which represents here the charging station. Then let's define the amplitude of the source. Then let's set the LLC duty cycle and frequency. Next step is to set the PFC frequency. We can then enable the control. As you can see, PWM generation occurs, and we can see that the current and voltage for the load are correctly generated. User can also load predefined scenarios for the load, which represents here the battery pack of the electric vehicle. Let's now have a look to the second user interface. This user interface is for the user to monitor the signals inside the controller. We can see, for example, the current and voltage of the boost converter. This is important to make sure that the signals from the simulator are received accurately. Let's now have a look to the third interface, which is the scope view interface. In this interface, user can monitor in detail measurements directly from the plant model. To start the acquisition, let's click on the play button. We can see here, for example, the voltage and current of our AC station. We can then see the voltage and current generated by the onboard charger for the battery pack. In the second screen, we can see the switching signals. In the first graph, we have the LLC converter switching signals, 2 PWMs, and in the bottom graph, we have the PFC PWM. In this user interface, we can see detailed waveforms directly from the FPGA model. We can see and monitor the PWM signals generated by the controller. This was our real-time simulation of the onboard charger. I hope you enjoyed it. Please contact us if you have any question at opal-rt.com.